All right, so today I'll be talking about optimal transport, and specifically, my talk will be structured similar to Leon's wonderful talk a couple weeks ago. It will be structured in two parts. The first part will be a slightly more applied approach to optimal transport, not because applied math is easier, but because we have better intuition for it. And the second part will be slightly more pure. And in the first part, I'll try to set up the basic problem, and then in the second part, we'll get to more abstract theory. Okay. So the basic premise of optimal transport, the basic theory of optimal transport started in the 1780s with this guy named Monge. So we have this thing called, I'll try to refrain from writing in cursive. So the Monge problem. What it is, it's that we have some distribution of, Monge was dealing with mines and factories. So we have some distribution of goods in the ground. So suppose that this is just the linear ground, and we have some distribution of, say, ore in the ground like that, right? And we have some distribution of places that need it. So some distribution like this, suppose this is like an industrial center, there's factories concentrated there, but all of them. So the idea is, the question is there some way, what is the optimal way of getting all the goods to the factories? And in this case, so this is the basic model. So the more realistic scenario, which we can't deal with right away, but we will be able to deal with in a little bit, maybe, is where you have a plane, so like a graph of the country, for example, and then you have the density of raw materials throughout that country. So I'm just going to use level curves, so you can imagine this being like a surface coming out of it. But so suppose there's lots and lots of like iron ore here, and you're fighting like World War II, and you need lots of iron. Suppose there's lots of iron ore here, and then like smaller deposits around here. Right? And then your industrial center's over here, so you need some transport map to there. Right. So this is the more realistic problem. And we'll see later that actually these sorts of problems come up, but with a lot more than 2 dimensions. And the reason that is because we can abstract away from actually just physical 2 dimensions. Okay. So what sort of conditions do we need on this transport map? So we want it to be optimal, but we'll talk about what it means to be optimal in a second. Most importantly, though, is simply that we need what's called the mass balancing property. So there's 2 types of mass balancing properties, the global and the local. What that means, very simply, though, is just that the amount of mass here all needs to go over here, right? Like you can't destroy mass, you can't leave it behind, no, right? You have to have the total mass here is the total mass here, or the total volume is the total volume. So we're going to call this set, give me a letter, R, okay. And then we'll call this one Q. Okay. So volume of R has to equal volume. Okay. This is a mass balancing property. Specifically, it's a global mass balancing property. Okay. But also, we have to have a local mass balancing property. Specifically, the amount of mass that gets sent to, say, here has to be the same as the amount of mass that is sent there, meaning that all of it has to get there. Okay? So let's just call this set A, right? And suppose that what gets sent there is from 2 different mines over here. And so these are just the pre-image, or T-1. This is an inverse pre-image of A. Right, so those are just 2 parts of the same set. Okay, and we need the mass that gets sent to be the same as the mass that gets received. Otherwise, we've lost something along the way, and that's really bad. And so we just need for all intervals, so for all A, B, we need volume of property. Now you notice that actually the local one includes a global one because you just take the whole interval. And we're assuming compact support, which in this situation what this means is we're just assuming that you have like a finite country, right? You don't have an infinite country because otherwise you would not be fighting any wars. So the mass balancing property is the first thing that we need on our optimal transport map. But there's a second thing that we need. We need it to be optimal. So what does that mean? So it's expensive to transport stuff across land, and what Monge, across distance rather. So what Monge's first problem, what he was looking at, is he was looking at, well, the amount of mass times the distance is equal to the cost, right? Because it's more expensive if you, in essence, the more work you do, right? Because in physics, work is distance times mass. But yeah, so it's more expensive to send more stuff, and it's more expensive to send it over longer distances. So the cost function between a point x and a point y, x is in our origin, and y is where we're sending it to, is the distance, x minus y, times the mass, which we'll just denote as a function. Right. Okay. And moreover, we care about the cost over everything. So we want to integrate. We care about the cost over all of x. And notice that y here is actually a function of x, right? Because we have our map t, which we take x and then we send it somewhere, y. So another way of saying this is c of, we want the integral over all of our set R. The integral of x, xt of x, with respect to x of course, is equal to the integral of, over our set R, of, well, this, which is just x minus t of x, rho of x. Right. So this is an energy. If you think about like an energy, we're minimizing an energy, it's a cost, same idea. So I'm just going to denote with epsilon of t. So it takes a function, an optimal transport map, and gives us a cost, or gives us a number. So it's functional. And what we're trying to do is we're trying to minimize this. So let me define an optimal transport map now that we've sort of set it up. So what an optimal transport map is, it's a map that balances mass. So T star is an optimal transport map. So if and only if, because it's a definition, if and only if it has the following two things. Number one, it balances mass. And then two, so it balances mass, and then the second thing it has to do is minimize the energy. It has to have the minimal energy. So the way that we write that is that T star, that the energy of T star is equal to the infimum. So this is the convergence point of the sequence of small things. It's like, you can think about this just as a minimum. The infimum of the energy functional over all possible transport maps, so over all T possible. Right. So that's an optimal transport map. Where am I at? Okay. Any questions so far? Is that up? Okay, so this problem with this cost actually turns out to be extremely hard. As a matter of fact, the problem with this cost wasn't really solved until 1980, and this was posed in 1790. And it wasn't proven that there always exists a map until like 1980, and it turns out that that optimal transport map for this sort of thing is not unique. And you can just think about that sort of interestingly. If you just have a set of 4 points on a tetrahedron, and you're, well, it's a bad tetrahedron, but you get the picture. You're trying to transport these two into these two. What's the optimal way of doing it? Any transport map is optimal, right? Because the tetrahedron is equidistant. So that's actually a really hard problem. It turns out that there are other cost functions which are much, much better. So it wasn't until, we're going to talk about this in a little bit, but it wasn't until the 1940s that we figured out a better formulation of this problem with a more, that allowed us to really understand it deeply and then solve its use with other cost functions. And we're able to actually solve it. So Munch sort of failed in that sense, but he was looking at like, like literally like just discrete points, not distributions like this. And so he was able to do like numerical methods that we otherwise couldn't do. Okay. So, great. What I want to do now is now that we set up the problem, I want to give some other applications, right? So the Munch problem we've been talking about is like minus factories. That's sort of very straightforward. But there are lots of other applications in general. So, and here you'll see where we use higher dimensions. So the natural place where this arose is economics, right? This is an economics problem fundamentally. And there are actually lots of other economic applications to it. So the other one is just like a general market. So a general market tells you that you have a certain amount of suppliers and a certain amount of demand, right? So in this case, you have, let's say your market is in a plane. Well, I don't think it's terribly important. You have some suppliers, right? And then you have consumers. Okay. Now, the question is, what's the cost function here, right? If it's just distance, then it's the same problem. But actually, it turns out that if you make the cost function value, like the value of the product, then what you end up doing is when you optimize this, you end up with equilibrium pricing. So this problem is actually equivalent to solving an equilibrium pricing solution. And as a matter of fact, the man that we're going to talk about next, Kantorovich, he was a Soviet economist who reformulated this problem and then was able to solve it. And for a very long time, no one in the Soviet Union worked on this because the fact that it was seen as markedly anti-communist, anti-Marxist mathematics because it had to do with equilibrium pricing. Yeah. Okay. Another interesting application which I personally don't know very much about. By the way, I posted onto the event page for this. I posted a ton of references and further reading. So I'll be like referring you to those. So in one of the talks, the person who's giving is the economist, and he mentions this really interesting application. So if you take people, and suppose you're looking at heterosexual marriage, right? So if you take people, you can parameterize them by all sorts of stuff like income, gender, income, gender, age, all these sorts of things, right? And it turns out that if you find some good cost function, so the cost function in this case would actually be like how much people value being married to another person, right? So like being married to someone who makes less than you would cost more than being married to someone who makes the same as you or more than you, and so on. If you find like a good cost function that you actually get like stable marriage pairings, it's similar to what we observe in actual real life. And apparently one of the part of the work that one of his colleagues did was that in theory you can parameterize men by one variable, which is income, and women by two, which is age and income. And there's like some standard cost function which actually like almost perfectly shows like what we actually observe in real life in terms of marriage pairings. So yeah, so that's entire book, which I posted, makes me a little uncomfortable, honestly. I'm not too sure I like that, but so it's mathematics. Anyway, so there's a book that I posted, which is Economic Applications of Optimal Transport, and it goes like in very detail through a bunch of these different applications. Okay. So in order to be able to do more with this problem, though, we have to like reformulate it in a more abstract way. So the thing that we're going to do is we're going to introduce a little bit of measure theory. Naturally, here we were talking about functions, which were sort of distributions over space, right? Well, another way of thinking about that is simply like how dense is like 4, for example, in a given space. So the natural concept that we're to use there is a probability measure. Let me talk about that. So a function u, which takes a set A and gives you some number, some real number, okay? This thing measures a set. And so if this always gives you a positive real number, and you have some other properties such that like an empty set has size 0, an empty set has size 0, and then if you have some smaller set, so B subset of A, that's going to be less than or equal to the size of A. Right? This thing is a measure. And moreover, if we want to make it, if we want to just talk about dense, so we can think about this like, okay, how much mass is in the set A, right? How much ore is in the set A? But if we want to think about this in terms of densities, how dense is the ore in the set A? We just have to divide by the total mass. So what we want is simply that of our entire space X, the mass of our entire space X is just 1. And you'll notice that this actually solves a really important problem, because then we have automatically mass pairing. Because both of the distributions will be of size 1, and so all we have to worry about is the local mass pairing. Okay. So what we do is we just reformulate this problem in these measured theoretic terms by taking integrals with respect to these. So what does that mean? How do we take an integral with respect to a different measure? So when we take a regular integral, we take the length of the interval, just sort of like standard Riemann sums. We take the length of the interval times the height of the function, and we get this area, right? Whenever we take an integral with respect to these measures, what we do is we just scale it by the measure. So this is in the second half of the talk, I'll probably talk slightly more details about when this works. But in general, we shouldn't be too concerned about it. What we do is simply just take the standard measure over this thing, and then just scale it by like so times like u of A, right? And then we get that the places that are more dense end up with more area, and the places that are less dense end up with less area. And so we can rewrite our cost function like that, right? So well, we can rewrite everything like that. So the first thing that we want to do is we want to rewrite the following property. So for all sets, for all open sets, doesn't really matter, also a subset of our entire space X. But then what we do, I forgot to sign. Okay, so we're trying to transfer from space X to space Y, right? And then we want two densities on them, right? The density of the ore on one of them, which is mu, and then the density of the ore on the other, which is like E, or eta. Okay, so what we want to do is then we want to have the same sort of mass preserving property, right? That whenever one gets sent to whenever a set with a certain density gets sent to another set, right, the density stays the same, meaning that like I don't lose ore, the ore gets sent everywhere it needs to. So the way that we write that is that if we have some transport map T, that the size of the preimage of any set A is equal to the size of A. Right. Does that make sense? So this is the most important property in terms of math, in terms of preserving math. And in this is actually called the push forward. The push forward measure. So V of A would be equal. We just write it like T upper star. Okay. That's just an notational thing. Okay. So then we have to sort of rephrase how we talk about optimal as well. So optimal transport, we have this integral of a cost function here. But our integral cost functions is going to be similar, but we have to take into account these densities now. So so what we did here was sort of clever. What we did here is we multiplied the distance, which was our part of our cost, by the mass, and then integrated, right? What we did there is really we took into account the density. By multiplying by the mass, we took into account that some parts are heavier and some parts aren't. But whenever we have these measures and we're integrating with respect to them, that happens automatically. We automatically multiply by how much is there and how much isn't. And so we don't have to do that anymore. And so in our case now, we can reformulate the same integral, for example, as the integral over a region x of x minus t of x d the measure on. Right. And for nice measures, meaning all the measures we care about usually, what that ends up being is the exact same integral we had before, which is x minus t of x times the mass. Yeah. Right. So it sort of seems like this is just a lot of reformulation for no purpose. But the reality is that if you're trying to solve these problems that have to do with the minimization of integrals, you really, really need to do this in terms of measure theory. Because measure theory meaning that you talk about these integrals with respect to densities. Because if you don't have, like the tools that you have in calculus just don't have the teeth to handle any of these problems. Which is probably one of the reasons that like Monge probably could not have solved this, even if like he was, Leonard Euler or something, Euler or something. Like he could not have solved this because the tools available to him just did not have the teeth. Like measure theory was really developed only in like the late 1800s, perfectly like rigorous in early 19, all the way to like early 1920s. I'm not a historian of mathematics though, so don't quote me on that. Anyway. Okay. So Louis Scacarelli gave sort of an interesting way of thinking about this problem. Well, it's not original to him, it's actually from the 1940s, but he came up with like a nice sort of story to go along with it. So suppose I were to take my two spaces and draw x and y. Oh, probably the other way around, because that's what we use. X and y. Okay. And then I were to have my densities on x and on y. On x and on y. Right. So the question is like, how can I transport from x to y optimally? And the answer is the same as the answer to the Monge problem. But what let me try to get this one. So what the Soviet mathematician I was telling you guys about, think it's like this. Okay. But the important thing, we're just going to abbreviate this. So the reformulation of this problem takes this form, right? It's the Monte-Cantovoric problem. The idea is that you can set up, you could write, you can sort of write x here and y here and put your probability distributions on either side, or your density distributions. And the idea is that instead of having like a perfect map that tells you, okay, from here you have one point which goes directly to here, right? Instead, you can sort of split up where that point goes, right? Because if you think about it in real life, if you have one factory that's sort of equidistant from two cities, the factory's output is going to go to those two cities roughly equally, assuming that the cities are the same size and everything, right? And in the original formulation, we couldn't do that because one point had to go to, every point had to go to another y point, and all of its mass was transferred that way. In this situation, it's sort of different. Instead, you say that like there's a certain amount of mass here. So this point in y, you're transferring from x to y. So a certain amount of your mass from x gets sent to this region, and a certain amount gets sent to this region, right? And as a matter of fact, you can do this over all of x. And what you end up with is a set of curves, or a surface on top of this xy plane. It could look like this, it could have lines, that sort of thing, right? And the idea is simply that at every single point, you just look across, and a certain amount of your stuff is going here, and a certain amount here, and everywhere else, none of it's going, right? So like this, you can set up an optimal transport problem. But what's interesting is that this is another distribution, right? But it's a distribution over different space. It's a distribution over the Cartesian product of our two original spaces. And so what we end up using is the tools of product measures. So what Cantovoric did was he said, if we can find a suitable product measure, meaning a suitable measure over the product of spaces, then sometimes that will give us a solution to the Monte problem. And if it doesn't, it means that the Monte problem is sort of unsolvable in that case. This always exists because you can just sort of take the trivial one where like you take literally, you multiply these two at the in size, and that's how high it is at this point. So there's always one. But the question is like, does that give you an optimal transport map? And the answer is no, in general. So it does give you an optimal transport map sometimes. And as a matter of fact, in a lot of times, it really does. And so let me just write out a little bit of that. So an optimal transport plan, so let me define this. So definition. So an optimal plan. Okay. So remember before we had optimal maps, but this is bigger than a map, it's a plan. They just sort of by analogy. An optimal plan is a measure on x cross y. It's a measure on x cross y, such that the integral of the cost function with respect to that measure, so is a measure, let's call it gamma, lowercase gamma, such that the integral of the cost function with respect to that measure is minimal. So what that means is that we're taking now, instead of taking the cost over paths, we're taking the cost over everything. And notice that if we don't have to travel, say this point doesn't, this is 0 here. If we don't have to travel, then the integral of the cost is 0 because we don't end up going there. But if we do have to travel, then it's going to include the travel cost for all of the places that that mass gets sent, but only scaled by the amount of mass that we end up sending there, which is exactly what you want. So this is the more general optimal transport problem, and we know it always has a solution, but the question is, do these solutions align? And the answer is, it depends, surprisingly, on what your cost function looks like. Even more surprisingly though, it actually doesn't depend so much on your cost function, but instead the support of your cost function. So what does that mean? So the support of your cost function is the values on which your cost function is not zero. So your cost can actually be negative. So if your cost is actually you're willing to someone's willing to pay you, for example, to transport something there, as opposed to like you have to pay for the transport, then your cost function will be negative. But the idea is just that the places where your cost function is not zero, so sub 2t's of rather the support of your of any. So some function f is a set of values x such that f of x is not equal to 0. Now notice that our support has to be finite, or it has to be not finite, but it has to be sort of small in some sense. Because if it weren't small, then we couldn't divide by the total amount of volume, right? Because there would be infinite amount. So it has to be what we call compact, which just means that there is some sort of, in the real case, it's finite and bounded. So it turns out actually, so this is a theorem which I won't prove, but it's sort of amazing that if the support of your measure, meaning if you look at this, all the places where it's not zero, if that support is convex, then the solution has, then the Monge-Cantorich problem has a solution, and that solution is also a solution to the Monge problem. And the convexity, you might be surprised by that, right? Convexity doesn't really have much to do with any of this, but it turns out that it actually really does have a pretty deep connection. And you can think about this in two ways. Number one, functions which are over convex sets tend to be differentiable, right? So if you have a function that's over, that who is non-zero on some really weird set, it's not going to be differentiable. But if it's non-zero over some nice set, you have a higher likelihood of it being differentiable. So that means exactly, you can hear the second part of the talk. But more interestingly, you can just think about the finite case. So if you have the finite case, say you're trying to take this, you're trying to take this amount, there's some amount of mass called, let's say 10, right? You have 10 mass here, and you're trying to send it to these 3 points, and the demand is like 8, 1, 1, right? There's obviously like an optimal map here that's just 1, 1, 8, right? And the cost might just be the difference between demand and supply, right? The inefficiency in the market. Well, if you think about it, a map is optimal if and only if you change any of these values, the map costs more. There's a bigger difference between supply and demand. So the most efficient map will be optimal in this sense. And it turns out that if you're talking about continuous functions, if you have the same sort of setup, the same thing is true. If you just take a finite number of points and you look at how much they cost, if you take a finite number of points and you look at how much they cost over the optimal transport map, right? It has to be minimal. If you switch any of the points around, then it will cost less than or equal to, or cost more than or equal to, right? And the idea here is simply that if this set were not convex, then you could have a situation like this. So this is outside of the set, and this is the inside of the set. You could have a situation like this, right, where the optimal transport is here, and the optimal transport might be here. And when you switch them, the cost actually might change, might go down, right? And so in that sense, it wouldn't be an optimal transport map, but you would have some like optimal distribution. So that's why convexity plays an important role here. And the final part of what I wanted to say for this half of the talk is simply talking slightly more about like some applications. So now that you have, so now that you have some very like general setup, now we can talk about what Caffarelli's story. So if I have this distribution and this distribution, and I need to transport one from one to the other, now I can try to figure out exactly what the optimal transport map is, or the optimal transport distribution is, and then like try to figure it out perfectly, right? But then suppose that like another mathematician comes to me, like let's say Juan comes to me, and it's like, hey, I will transport this for you, okay? And it doesn't matter to me what transport map, it doesn't matter to me what transport map he has, it just matters to me the price, right? It matters to me the price. And he says, okay, I'll give you a price based upon how much is here and how much is here, right? So at any x point, I'll give you a price per mass. And at any y point, I'll give you a price per mass. And then you just integrate over all the prices and integrate over all the prices, and that's your total price. Okay. Now notice that nothing about the transport comes in there, right? But if Juan is able to do this, if he's able to give me a price from one to the other, then that price has to be less than, or sorry, that price has to, if he's going to make some sort of profit or at least break even, right? That price, my total price has to be slightly more than the price that it would cost me to do it myself, right? Otherwise, I would just do it. So if Juan gives me a total price, that price has to be less than or equal to the amount that it would cost me to do it myself. Otherwise, I would just do it myself and have to figure out this optimal transport map. Well, it turns out that these problems are sort of related. Like the pricing problem and the optimal transport problem are like pretty deeply related. So there's a duality. This is called Cantor-Borch duality, and the duality is the following. So suppose that I have a price 1 for every x point, okay, and I have a price 2 for every y point. Okay. If I minimize this, so it's such that at every single point, x and y, the price is less than it would cost me to do it myself, meaning it's less than the cost x, y. So if I solve this problem, like what is the optimal price, it turns out that I've solved the other problem as well, right? Because in order to figure out an optimal price, I have to figure out how much it costs me to transport given any x or y. And so this condition implies that this is going to be less than or equal to the cost for me to do it myself, x comma y over, okay. So this is the dual problem. And the question of optimal pricing is exactly as hard as the other question. And it turns out that in most cases, these are actually equal, right? So you have to find like a slightly rigorous theory of like, well, when are these equal, when are these not equal? And if they're not equal, it's said to have a duality gap. And if you think about it in the way that Caprelli told the story of like, there's someone trying to transport and there's someone giving prices, it's a very economic thing. And as a matter of fact, what this shows is that a central planner, okay, has to figure out the exact same information as the market does whenever it gives you prices. And as a matter of fact, when the market performs more efficiently than a central planner ever could, like possibly, there's a duality gap, right? Which means that there's some sort of like mathematical theory of when markets have to perform more efficiently than centralized governments, right? And now you see why it's anti-Marxist. So the so there's a pretty rich economic theory here, but mathematically this is also super useful because this problem of trying to optimize these can be much easier in certain situations. And so if you look at the dual problem, so this is sort of like a general theme in mathematics, is that sometimes whenever you find one problem and you find a dual problem that are equivalent sometimes, the dual problem is very often much easier. And in this case, this is a situation where like that's sometimes true. Okay, and that's the end of the first half of my talk. Ideally, we should have pizza. But we don't. Should we chill until we have pizza?
Ideally, we'd have pizza, but we don't.
Yeah.
Story about it.
I wonder what food efficiency cost that. So the second half of my talk is going to be different than the first half. It's less cohesive, but it's going to show it's going to show, like, to use a pretentious term, it's going to be like a vignette of how optimal transport interplays with different areas of mathematics. So I'm going to talk about three different things. First, well, not first, three different things. I'm going to talk about how optimal transport interplays with analysis. So Zachary and I were just talking about this, but how optimal transport relates to the regularity, meaning how smooth certain solutions to particular PDE, partial differential equations, are. So I'm going to talk about where that comes from and what we know about it to some extent, to the extent that I know about it. And then I'm going to talk about I'm going to talk about optimal transport and Riemannian manifolds. This is what Juan brought up. What spaces are we working over? Does this only work over Euclidean space? It actually works over more general spaces for Riemannian manifolds. And then the last thing I want to bring up, which is similar to another question that was asked, is how this relates to isoperimetric inequalities or problems of minimal surfaces. So isoperimetric means that you take the same perimeter, how much area do you close? So minimal surfaces. Okay. I'm probably going to do them in that order because that's the order of like prerequisites. So the first thing I want to talk about is sort of these solutions. So in the last part, I said that the solutions to the Munch-Cantor-Borek, I should really learn how to pronounce that part again. Stop. The Munch-Cantor-Borek problem. These solutions exist, right, for because of some property of convexity. So, like, what does that mean specifically? Well, there's this theorem by Brenier, I think it's called. There's a theorem by Brenier which says that specifically, if you have convexity on, that specifically you have, so for the following cost function, so if your cost function is c of xy is equal to 1/2 the distance squared. Okay, so this is the cost function. Now notice that this is very similar to the last cost function we had, which is just straight distance, but this is distance squared, which is actually a much nicer function if you think about it in terms of how it behaves with integrability. It's a convex function, and so on. If you want a heuristic and need a lower functional, right, this is why like L2 behaves much nicer than L1. It's honestly like Hilbert space, not just a Lozano space. If you don't know functional, get one of that. So Bernet says, I think this is how you spell it, although I can be completely wrong. So what Bernet says is that if you have this cost function, then the solution to the optimal transport problem will be, well, you'll have, the first big thing is that there exists optimal transport map. And then the really important conclusion is that this map takes a particular form. Specifically, the optimal transport map is equal to the gradient. So, like, what do I mean by gradient? I'll tell you in a second. Is equal to the gradient of phi, where phi is a convex function. So here, I mean something slightly weaker, right? So so there's this optimal transport map with respect to some measure. So with measure, yeah. Right. So what I really mean here is mu is gamma almost everywhere, right? So this thing's equal to a gradient on all but some like tiny set of points that has measures here. So it's literally almost everywhere equal to the gradient of some convex function. And so, does everyone know what a convex function is? No?
It might be good to write down a definition.
I don't remember a definition. All right. Anyone have a good definition of a convex function?
In what generality?
Any generality.
I mean, I think basic example is if you take a convex linear combination of inputs, then it's less than or equal to, like, what is it? Well, like if you're dealing with like a one dimension or a function of one real variable, right? And it's like f of lambda t plus 1 minus lambda, or f of, what is it? Lambda x plus 1 minus lambda y is less than or equal to lambda f of x plus 1 minus lambda f of y. It's like you can pull the convex linear combination from the inside to the outside. Does that make sense?
Like this?
No, like, it's like you're looking at, what you're putting in as your input is like lambda times x plus 1 minus lambda times y.
Oh, you're like linearly interpolating?
Yeah, I mean, yeah, that's a convex linear combination of x and y if lambda is in the interval 0 to 1.
Right.
And then if you look at f of that, for example, that's less than or equal to the corresponding linear combination of f of x and f of y. So there should be a lambda on this.
Right, I see. Because it's linear, yeah.
But is that what it is in general? I mean, that sort of thing?
Yeah, so there's a general definition that looks sort of like this, which I don't remember off the top of my head, unfortunately, I didn't write it down, which is like this, but for measures.
Okay.
Yeah. Okay, whatever. A convex function is a function, like we literally, actually let's instead take this to be Lipschitz functions, right? It sort of works for Lipschitz functions. There's slightly more like almost everywhere, but I know what a Lipschitz function is, so don't worry. So everyone know what a Lipschitz function is? Okay, I'll write down the definition of that. So a Lipschitz function is a function such that f of x, so for all x, y, right, f of x minus f of y is less than or equal to some constant called the Lipschitz constant, so const times x plus y. For any, this works for any dimension. And functions from like R to R. So this Lipschitz functions. Lipschitz functions are not convex, but convex functions are Lipschitz. I think that's how that works. Okay. Anyway, this theorem holds for Lipschitz functions. So what's interesting about this theorem? So this theorem tells you some really nice structure of the optimal transform map, right? It tells you that the gradient is a complex function, or in our case, the gradient is some Lipschitz function, right? But it also implies something, and I don't know who first. These are not my notes. I don't know who first noticed this actually, but it's really interesting. There is so the gradient of a convex function is itself differentiable almost everywhere. So that's a byproduct of Rademacher's theorem, which tells you that Lipschitz functions are almost everywhere differentiable, and convex functions are Lipschitz. I believe. The theorem is true. I don't know how. I'm not sure that that statement is true. Anyway, so theorem. The gradient of phi, where phi is complex, is almost everywhere differentiable. Almost everywhere differentiable. Okay. All right. So this implies that something sort of interesting, that there's this equation called the Monge-Ampere equation. And what it says is that the determinant of a Hessian, so remember that, it's the determinant of the second derivatives. It's the determinant of the matrix to f of x over g of the gradient of u, okay, for almost all f, for given like any f, and you need some some conditions on g. Okay, so this is the Monge-Ampere equation, and the regularity of its solution. So it turns out that this thing has solutions if g is convex. So who proved that? Luis Caffarelli did. It's a pretty old theorem, I think. He proved it in the 80s, maybe. Anyway, but Luis Caffarelli proved that there's an obstruction to the regularity of these solutions. So what does that mean? There's an obstruction to there being solutions that are sufficiently differentiable. So here you need at least second differentiability. If g is not convex. So you have some function of g that's convex. Okay, so what that implies here is that given some g convex, you have you can substitute in the optimal transport map because it's the optimal transport map is the gradient of some phi, and so that implies that we're just going to literally substitute this in. You have a new differential equation, determinant of the gradient of the optimal transport map. Does that work? Yeah. Is equal to f of x over the same g of the optimal transport map.
What is this x in this equation?
Oh, x is the so x is like where like it's a function. It's the same thing as these are all functions of x.
Okay.
I'm just suppressing the x's for notational ease. But like this is a function of x. This is a function of x, and this is a function of x. Everything's a function of x. The optimal transport map is a function of x. Right. So yeah. Anyway, but what that implies that if you have some optimal transport map, then it works as at least halfway to a solution to the Monge-Ampere equation, right? And moreover, because you know that the optimal transport map is sufficiently differentiable, specifically it's second differentiable. The optimal transport map is differentiable, so the complex function is second differentiable. Almost everywhere. What that implies is that you have a solution here, and that implies that this is convex. Okay. The thing is that the theory of this equation is like much older, and there was this thing called Alexandrov solutions. So Alexandrov solutions are like weak solutions. So what they did is they would integrate both sides of the equation. So integrate this with respect to the dx in the standard Lebesgue measure. Right. And then the f of x was literally any compact supported function, a test function, whatever. And the idea was that if you had if you had a function such that the integrals matched, but it might not have been like necessarily as differentiable as you needed, meaning that like the points, like the area that you wanted to measure, right, was correct and matched up with these integrals, but maybe your function wasn't as differentiable as you needed. And so here I'm suppressing some like important information about like super differentiability. But yeah. Anyway, so these are they're weak solutions, but they're not differentiable enough, right? And we know that like weak solutions can't be optimal transport maps because optimal transport maps have to be second differentiable. Right. So the question of like finding optimal transport maps is equivalent, not exactly equivalent, but the question of finding optimal transport maps is a subset of the question of finding which Alexandrov solutions are actually solutions, which of them are not simply weak solutions, right? And so in that way, you get a problem in the regularity theory of partial differential equations, which is completely analytical, not very based on optimal transport. And one of the reasons that Luis Caffarelli has published so much on this subject is because it is like such an analytical thing, even though it has all these implications in optimal transport. Okay, so that's it for analysis. Any questions about that? Okay.
Not a question. It was great. I gotta go.
Okay, and then And let me talk just briefly about the stuff on manifolds. The same sort of ideas of optimal transport hold over more general spaces than just Euclidean space, right? So they hold over what are called Riemannian manifolds. So I'm not going to define this for you because the definition is like not worth it in a lot of ways. But let me just tell you what's sort of important. So in mathematics, there's like lots of different spaces you can study, and one of them, there's the general idea of manifolds, right? So manifolds look locally, meaning that they have open neighborhoods that look like Euclidean space, right? And they're manifolds whose maps, so there's a map from Euclidean space to that open neighborhood, right? Those maps can be different amounts of differentiable, right? So there's manifolds that are not differentiable at all, those are just topological manifolds. Then there's like Cn manifolds, which are n differentiable. But then there's also something that's sort of interesting, which are variables, which are almost everywhere differentiable. They're not differentiable at all the points, but they're almost everywhere differentiable. So these are weaker. They're still stronger than manifolds. Okay, but the problem with all these types of things is that they don't preserve a lot of the stuff we care about. Specifically, we've been talking all this time about measure theory, right? Measure theory is all about volumes, but none of these manifolds preserve any sort of volumes, right? They don't have what are called volume forms because differentiability is not a strong enough condition. To actually have volume preservation, or in essence, to even have a notion of like suitable volume, right? Because if we think about like two manifolds, when are they equal? Well, a natural thing might be like, well, they're equal whenever, if I take a square on one, it's going to be the same area as a square on the other under some suitable map, right? But differentiable manifolds don't have that property. So instead we need Riemannian manifolds. So Riemannian manifolds are differentiable manifolds, they're at least C1, which also have an inner product on them, which lets you measure angles. So Riemannian, so these are differential, like diff top. These are differential topology, but these are like really geometric, right? And once you have that geometry, you have the optimal transport problem. Okay, and that's all I'll say about that at like a really elementary level for, I suppose, Zachary and a couple other people who know what Riemannian manifolds are. Let me say this: whenever you have a Riemannian manifold, you have what's called a geodesic distance on it, right? And it turns out that if your cost functions are geodesic distances, okay, instead of just like standard Riemannian distances, right, you have your geodesic distances, then because the sectional and Ricci curvatures come entirely from that from the geodicity of various curves to your points, all the information about sectional curvature can be encoded in the smoothness of optimal transport maps using geodesic distance. And all the information about Ricci curvature can be encoded using the optimal transport maps of entropy. Right, so it's
Sorry about that, guys.
Thank you. Okay, so you have these things called entropy functionals. So this is, the reason I say this is because like, number one, I think it's really cool. Right, so you have entropy functionals which look like rho log rho, right? And you're taking this with respect to like some sort of like Riemannian distance, so you're looking at like dv, like some wedge product of stuff on the tensor algebra of the cotangent bundle, right? Whatever, not important. You have entropy functionals, right? Entropy functionals encode all the information about Ricci curvature. And it was actually improving something about entropy functional, like specifically proving something about like a minimal curvature. So you can bound the curvature of the Ricci curvature of a manifold everywhere below if you have some information about the solutions or the minimizers of entropy functionals, and Cedric Villani did that, and he won the Fields Medal for it. So, yeah. Okay, and then the last thing I want to say is about isoperimetry, which I sort of talked about already, but, oh, by the way, let me point you to references. So if you want to read more about Riemannian manifolds, there's a lecture by Villani, which talks about regularity, which I posted, and there's also notes by maybe Fagali, maybe McDonald, I don't know. What?
They're on the Facebook
On the
page.
Facebook.
On the actual event.
On the event, yeah. So which say like they're an overview of optimal transport in differential geometry and differential topology. So if you want to read more about that. The last thing I want to say is about isoperimetry, which is the paper by Maggi and Fagali and the person whose name starts with a P, whose name I can't pronounce. Their paper talks about isoperimetry, and I already sort of gave away the result, which was that like if you have a minimal surface, you can use these the methods of optimal transport to figure out whenever you're trying to minimize an energy functional, which a surface always does. A minimal surface always does. If you're trying to minimize an energy functional, then what ends up happening is that you can actually bound how much your area changes given a slight increase in energy, and it's always bounded for sufficiently nice energy functionals for by the square root of energy added. Okay. The other thing I wanted to say about that though is that there's an entire, so Cedric Villani talks about this in his book, Optimal Transport Old and New, where there's this entire class of like isoperimetric inequalities, right? Like the Sobolev inequalities, the like classic Euclidean isoperimetric inequalities, all these different isoperimetric inequalities. And what they all pretty much say is that like they all say that like if you have, in a suitable metric or whatever, if you have a ball, right, you have any other set, right, whose perimeter is equal to the perimeter of the ball will always enclose more greater than or equal to the area. And what Villani points out is and which Maggi in his paper talks about in some detail, is that everyone has been able to prove this using optimal transport. And what's sort of interesting is that like the specifics of the optimal transport aren't so interesting, but because different optimal transport maps actually can prove the same inequality. But there's one inequality, which is called the Levin-Gromov inequality on Riemannian manifolds, which has only been proven using methods from geometric measure theory. And there is no proof, according to Villani, in this 2016 book, 2013 book. There is no proof using optimal transport. And why? So it's an open problem, actually, to finish off this project of proving isoperimetric inequalities using optimal transport. And there's lots of research going on in all those different areas. Okay, I think that's it. Questions? Yep.
Do you know anything about giraffe functors?
Nothing to do with this, but yeah, I do know about direct functors.
I can't. This is a